let's go ahead and get started for today. As far as announcements go, the general, just to kind of let you know, the general schedule is we'll take our tests on Thursday nights, and I'll do my best to get them to you on Monday. Right? That's kind of my normal schedule. So next week in lab, we're going to be doing Who Has My Clear Liquid. All right, so many of you may already have the pre-lab for that already completed, and that's great. But you may want to, and it's been 2 weeks, so you may want to look over and just make sure that you're familiar with what we're doing. You've got the apparatus drawn out in your notebook, so you can put it together really fast and be ready to move. All right. And I don't know that I have any other announcements. Does anybody else have a question? Yeah.
This was a while ago for the IR spectra that
Mm-hmm.
you noticed Tuesday. Because I don't know if like the finder wasn't out.
For the IR lab, there's a pile in the lab, or there was a stack in the lab this week. So if you just give it to me after class or something, I'll get it put back. Other questions? All right, seeing none, we'll move on to the next section, our next module. Finished up with our nomenclature on Wednesday. All right, so at this point, you have at least been shown examples of pretty much all the different rules there on the bottom of that sheet. And I would urge you to continue practicing. All right, the nomenclature is going to be a thing from now to the end of the semester, or the end of the year. And the faster you get it down, the better off you're going to be. I will go ahead and open up one of the competencies. It's a competency on basic nomenclature, and we'll get that up and going. And it's the basic nomenclature is an essential, so you'll have as many times as you need to pass it. We're going to get that taken care of. Our next section here is the last of our quote-unquote review sections. We're almost finished going through the 121, 122 stuff from last year. And we're going to talk a little bit about acid-base theory. And you've probably had, if you've ever had a chemistry class, there's probably been some section of acid-base chemistry as part of it. It's just one of those topics that keeps coming back over and over and over again. In fact, there's one organic textbook who approaches everything as an acid-base reaction. Like the whole course from beginning to end, every reaction, it talks about it from the perspective of acids and bases. Because it's not the most common way to do it, but you can think about it from that perspective. All right? So because it's such a foundational concept, I want to make sure that we're all on the same page here with regards to acid-base theory. So historically, we've got to go all the way back to Arrhenius. All right, Arrhenius came up with the first definitions of acids and bases in 1884. And he defined an acid as a substance that dissolves in water to form an H+, and a base is a substance that dissolves in water to form an OH-. Now, that definition works great until you recognize that, well, H+s can exist on their own. Right? You can't just have a proton. It's got to be attached to something else. And so the definition got modified so that it was anything that donates a proton in water to make a hydronium ion. Right? So that's more of the common definition that's used today. Still, the problem with Arrhenius is it requires water. And what have we learned so far about water and organic? They're not compatible with each other for the most part. Right? There are very few things that are actually water soluble in organic. And so the Arrhenius definition from an organic perspective isn't used very much. Now, in 1923, Bronsted and Lowry independently came up with the definitions that an acid was something that donates a proton, and a base is something that accepts a proton. And the great thing about the Bronsted-Lowry definition is that it removes the requirement for water. Right? The proton can be donated to anything. Right? And instead of having the hydroxide ion being formed, we're just talking about a pair of electrons going and grabbing a proton. So basically anything that has a pair of electrons that is available can be a base. So the Bronsted-Lowry definition is the one that we use the most with organic because we don't have that water requirement. Now, we always talk about acid-base pairs. An acid donates its proton and then becomes a conjugate base. Because where that proton was, it's going to leave behind a pair of electrons. And that pair of electrons can go and grab a proton and act as a base. Right? So we have this acid becoming a conjugate base. And then likewise, a base is something that attracts or adds a proton. And once it's done that, it becomes a conjugate acid. Because if you look at the reverse reaction, it's going to be donating its proton. Now, notice in this particular case, we're showing this with just a forward arrow. That's significant because that forward arrow means what? Everything is going to those products. It is not reversible. All right? And when we're talking about acid-base reactions, we're going to have to make sure we pay attention to that arrow quite a bit, because that arrow is going to tell us a lot. Now, from a curved arrow perspective, we can look at it as the electrons on the oxygen are going to grab the hydrogen, and notice that we're going to use that double arrow there, or that double barb there, to indicate that it's 2 electrons moving. And then these electrons here are going to the chlorine. And I myself am even usually a little more direct, and I put the arrow going directly to that chlorine. All right? Now, we call this curved arrow formalism the mechanism of the reaction. And we're going to draw a lot of mechanisms in this class, because the mechanism allows us to understand what's going on. It allows us to answer the question, why? Why does this reaction happen? So in this case, the electrons from water are going and grabbing that hydrogen. Well, then 2 electrons from the hydrogen, or they're forming that HCl bond, have to go somewhere. So they go and form a chloride ion. All right? Now, that arrow in the middle, in this case, it's going all the way to the right, which means it's not a reversible process. When we're trying to decide what that arrow is going to look like, we need to think about its acid dissociation constant. The acid dissociation constant is just a measure of how much it's going to dissociate in water. So here you have acetic acid and water going to form the acetate ion plus the hydronium ion. Now, if we were going to draw the curved arrow formalism for this, what's the first arrow that we would draw? Not the pi bond. All right. The water is going to be acting as our base, right? So it's going to go and pull off the proton. And then the electrons from this OH bond are going to the oxygen. All right? And so that forms our acetate ion along with the hydronium ion. All right? And when we're looking at that curved arrow formalism, we're looking at those arrows, we always have to have an arrow for everything. All right? We can't just have or hydrogens just jump from one place to another, or electrons just disappear. Now, the arrows here, what are these arrows telling us? Which side is favored, the products or the reactants? The reactants, right? Right? It's saying that this doesn't dissociate completely. In fact, if you mix acetic acid in with water, there's going to be a lot of acetic acid still around. It's very different than what we saw with the HCl, right? The HCl was an arrow that went to the right completely. So this is telling us that the acetic acid is a weak acid because it doesn't dissociate completely in water. And it's telling us that there's a big difference between the acetic acid and the HCl, right? The conjugate base that is being formed, in this case the acetate ion, is not nearly as stable as that chloride ion is. Now, from just a generic standpoint, we can say that HA plus water which in the previous case that was acetic acid plus water, or HCl plus water, is going to be in equilibrium with the negative ion, its conjugate base, along with the hydronium, the conjugate acid. All right, you see how we just did those substitutions to get the generic form of the equation? Well, we can write the KEQ for that equation as just being the hydronium ion times the acetate ion, the reactants, divided by the concentration of the products, HA and H2O. Okay? Anything up there look confusing? We're all pretty familiar with drawing KEQs, right? Well, the problem with a KEQ when we're talking about things like acids and bases is this guy here, the concentration of water. In most situations, the concentration of H3O plus we're going to be talking about is at best 1 molar. At best, you know, the strongest acid we've got is like 18 molar. And that's the strongest out there, sulfuric acid. You know, HCl is like the strongest concentration you can get is like 11.4 molar. Most acids we're going to be talking about 1 molar or less. Pretty small numbers. The A minus, again, the maximum is going to be the same as the hydronium ion concentration. And HA, we're talking again about a small number. All right, so we've got something that's small, 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 and then what's the concentration of water? If you've got it, it's going to be big. All right, it ends up being about 55.6 molar, and you just get that from the idea that it's 1,000 grams per liter. Right, that's equals 55 moles per liter. So if we're talking really high compared to all these other things. So the KEQ here, the numbers themselves are going to be all around 55.6. All right. And so that makes it a little problematic. There's not much differentiation there. And so that's where the Ka comes into play. The Ka, the acid dissociation constant, is just the KEQ times the concentration of water. All right? Or that leaves behind in the concentration of hydronium, the concentration of A minus over the concentration of HA. Now again, I hope you're seeing a theme. Do we have to have a Ka? Could we just do all this with KEQ? Yeah. But they're big numbers and they're all really close to each other. So it's hard to differentiate. Do we like things that are unwieldy? No. So if something is unwieldy, we just change it into something we do like. All right, and that's what we're doing here. That's where this Ka comes into play. Now, Kas as well are going to range from down around 0.00000, 10 to the minus something, like 10 to the minus 56 or so, all the way up to 10 to the 12th or so. That's a big range, right? Do we like things that are big and unwieldy? No. So instead of using Kas even, the thing we're going to use more often than not is a pKa. All right? And the pKa is just the negative log of the Ka. Now, that means that the pKa range is going to go from about minus 10 up to about 65. From about minus 10 to 65. So those are numbers that are a lot easier to work with, right? From minus 10 to 65, a range of 75, just they feel better. Instead of saying 10 to the minus 54th, All right? It's just easier to do it this way. Now, it does create a hiccup. If I gave you two acids, one had a pK of -7, the other had a pK of 25. Which of those would be the strongest acid? Meaning, which would have the largest Ka? The one that's the -7. Why? Because it's a negative log. So the larger the Ka is, the more it dissociates, right? The more it dissociates, the more it makes this guy, the number on top, bigger. The pKa is going to be smaller. So the larger the pKa, the weaker the acid. The smaller the pKa, the greater the acid. So our scale of pKa is going to go from like -10, which is where we're going to find sulfuric acid, all the way up into the 60s where we find alkanes. And our strongest acids are going to be the ones that have a strong acid by definition is going to be anything that's got a pKa less than 0. A weak acid is going to be anything above 0. All right? So we were talking about acetic acid just a few minutes ago, right? Acetic acid has a pKa of 4.76. So does that make it a strong acid or a weak acid? Makes it a weak acid, right? Because to be a strong acid, it has to dissociate completely in water, which means its pKa would be less than 0. So it's a weak acid. But know that you're going to probably hear me refer to this as a strong acid. And you'll probably hear me refer to it as a strong acid a lot. Because from an organic perspective, the carboxylic acids are as acidic as we get. All right? The strongest acids we know that are organic are the carboxylic acids. So while they are weak acids overall, from our perspective, it's the best we got. So you'll hear me say, yeah, we'll put a strong acid in. But you and I both need to know that means we're putting in a carboxylic acid, which is really a weak acid, but it's what we got. Okay? So let's look at some examples of some just good old pKas, just to kind of get a feel for where everything lies. All right, so we've got acetic acid there at about 4.7. And that's going to be a good number for all carboxylic acids, at least to start from. All right, most carboxylic acids are going to be around that 4.7 range. If you look there in that on this chart, it's got the sulfuric acid at -4.8 and the HCl at -3.9. I don't really like those numbers very much. All right, the numbers I like are -10 and -7. Sulfuric acid at -10 and sulfuric acid or HCl at -7. Now, the discrepancy comes because of what's written here at the bottom. The pK, it doesn't even say on here, does it? It's using here water as the solvent. All right. But the problem with water as a solvent is everything that is less than 0 is going to dissociate completely, right? So you can't measure it in water. They've got to use some calculations to get anything less than 0, or they have to switch to a different solvent. And the more accepted values for these guys are going to be -10 and -7. Like, it's known that sulfuric acid is stronger than HI. But yet on this chart, you can't see that. So the numbers I would memorize and learn is that sulfuric acid is at -10, HCl is at -7, then like HBr would be at -8, and HI at -9. All right, those numbers make a little more sense. There at -1.7, you see the hydronium ion. Right? The hydronium ion is where, the compound that's formed when we donate a proton to water. So you can think of the hydronium as being, and I'm just going to draw this with an R here, as a good example for an sp3 oxygen that's been protonated. Whether it's a water or an alcohol, they're all going to have a pKa of around negative 1.7 when they've been protonated. All right, so that's a better, that's just when you've got an sp3 oxygen hydrogen. Here you can see carbonic acid coming in at 6.4. That played a large role in that, or that'll play a large role coming up in a lab we're doing. Carbonic acid is what's formed when you take sodium bicarbonate and you react it with a strong acid. It forms carbonic acid. That's the acid that's formed or that's used in soda to give its fizz. When carbonic acid reacts with water, it forms carbon dioxide in water. All right, and so it comes in right there in the middle at 6.36. Here it's got it 6.4. Phenols, remember I said that when an OH is on an arene, it doesn't act like an alcohol anymore, so we consider it a different functional group. Here's an example of that. A phenol has an acidity of around plus 10. All right, phenols are at plus 10. Protonated amines come in at about 10.7. Ammonia itself comes in at about plus 9, but once you put that R group on it, it provides a little bit of destabilization, and so it comes up about around 10.7 or so.
These pKa numbers you're giving us, is this stuff we're going to need to memorize or just kind of have a feel for about where it's at?
I wouldn't say you need to memorize them. I would say you would need to know them well enough, like use them so often that they become part of the fabric of who you are. All right. Methanol, you see here coming in at 15.2. It's the strongest of all the alcohols. All right, so let's think about it. 16, water's 15.7, alcohols, ethanol 16. 16 is a good number for all alcohols except for methanol. So where did the phenol come in? 10, right? Alcohols are at 16. Now remember, these are pKa numbers, right? So it's not that there are, phenols are 6 times more acidic than alcohols. Phenols are 10 to the 6th time more acidic than alcohols. 10 to the 6, 1,000,000 times, right? Phenols are 1,000,000 times more acidic than alcohols. Right? So that's why they're considered to be a different functional group. Here at 19, we get acetone. All right, remember acetone has that carbon, really, it's a good number for just a hydrogen attached to a carbon next to a carbonyl. A good rough value for that is 19. Acetylene. All right, acetylene is a common name. We haven't talked about it yet, but acetylene is this guy. Acetylenes come in at 26. And what we're really saying there is a hydrogen on an sp carbon comes in at about 26. All right? Hydrogen on an sp carbon is about 26. Here you see the amines. All right? Not talking about the ammoniums where they're already protonated, but the amines, they're at about 36. Ethylene comes in at 42. Here it says 45. Okay. I skipped one here. Notice that it's got the benzene here at 43 and the ethylene at 45. In general, okay? Oh, I see what it's doing here. An sp2 carbon to hydrogen. All right, in general, an sp2 carbon to hydrogen, a good number for that is 45. Right? A good number for an sp2 carbon hydrogen is 45. For an arene sp2 to hydrogen, it's a little less than that, like 43. Okay? And then the alkanes themselves are up somewhere 60 to 62 region. They're our least acidic groups. All right? That we're dealing with in organic. So when we're looking at the pKa's for each of these, we're looking to see how easy it is to pull off a proton, right? Something that is more acidic, you can pull a proton off easier than something that's less acidic. What makes it so that some things are easier to pull a proton off of than others? Like generic terms, alcohol versus a carbon. The alcohols are at 4, 10, and 16, right? Or 08, hydrogens attached to oxygens. Carboxylic acid's at 4s, phenols at 10s, alcohols at 16. The first carbon we ran into was at 19. Then we had 26, 45, and 60. So why is it easier to pull a proton off of a oxygen than it is a carbon?
Electronegativity.
Electronegativity, right? Oxygen's more electronegative than carbon. So within this chart and these numbers, there's a lot of good stuff that you know already that's hidden, all right? That's kind of buried in there. Now, in general, there are 4 things that come into play when we're talking about these numbers. Right? The general idea is you're going to memorize or learn the key values. And then we're going to predict from that particular point where the actual value is going to be. Right? And so for the most part, these things that affect the pKa are hidden in these key values, or they're part of the key values. For example, like we just said, electronegativity. Electronegativity of the atom that's bearing that hydrogen plays a huge role. Oxygen is at 16, an amine is at 38, a carbon is at 60. All right? So you can see as the electronegativity increases, it's easier to pull off that proton. In general, what we say is that the acidity of a molecule is determined by the stability of its conjugate base. Let me say that again. The acidity of a molecule is determined by the stability of its conjugate base. So the more stable the conjugate base, the more acidic something is. So when we're thinking about electronegativity, oxygen, by nature of it being more electronegative, is more stable with a negative charge than nitrogen is. Nitrogen, being more electronegative than carbon, is more stable with a negative charge than carbon is. So the more stable the conjugate base is, all right, the O minus is more stable than the N minus, which is more stable than the C minus. So the more stable the conjugate base, the more acidic something is. And so electronegativity is a big thing that comes into play when we're talking about pKa's. And you can see several different examples of that in those numbers that I showed you a minute ago. The second thing that comes into play is the size of the atom bearing the negative charge. Right? The easiest way to think about this one to me is babysitting a child. All right? You need to go, or you've been asked to babysit a 2.5-year-old. Okay? What's going to be easiest? To babysit that child in a car, to babysit it in a house, or to babysit it in a park with a fence around it? Which is easiest? The park, right? You got more room for the kid to run around and play and get its energy out. You don't feel that stress as much. There's not that much tension there. All right, well, the more space an electron has to spread out, the less repulsions we're going to have, the more stable we're going to be. All right, so if we look at like methane thiol versus methane thiolate, or methanol, sorry. Methane thiol becomes methane thiolate, it's conjugate base. But on this side, we're talking about sulfur. On this side, we're talking about oxygen. Which is bigger, sulfur or oxygen? How do you know? It's down the road, right? And so sulfur is larger. In both cases, we're talking about the sulfur having a negative charge or the oxygen having a negative charge. Well, sulfur, by nature of being larger, is going to have more space to spread out that charge, and so it's going to be more stable. Okay? So this equilibrium you see lies to the right. Right. And just to help visualize that, you can see a picture here. On the left is the thiolate, in the middle is the methoxide, and then on the right you've got them sitting on top of each other. Right? You see that sulfur is almost twice as large as the oxygen. So it makes a significant difference there. And you can see that in its charge difference of 7 to 16. All right? 7 to 16 is not a difference of 9. It's a difference of 10 to the 9. All right? That's a huge difference. All right, you gotta remember these are pKs.
Would you say the arrows told us exactly again?
Like in this case, it's telling us that the reaction favors the right. So that means the thiolate is more stable than the methoxide is. And in fact, it's 1 billion times more stable. All right? What's up, Emily?
So it's better for the sulfur to have a negative charge because it's larger, but it's just that the oxygen is more electronegative.
Yeah, but the size makes a bigger difference. There's not that much of a difference in electronegativity between the sulfur and the oxygen. So the sulfur having more space wins. Okay.
So what if you have something like francium? See, I read something about like superacids, and I think that's what they would use. So would it be better for like the francium to have like a negative charge than something up there that's way more electronegative?
With superacids, you have to use a whole completely different set of rules. And so it's, honestly, it's not even relevant to this discussion, if that makes sense. The traditional rules are null and void. Okay? The third thing is resonance. And we see this when we think about ethanol versus acetic acid. Ethanol's pKa was 16. Acetic acid was 4.76. In both cases, we've got the oxygen bearing the negative charge. All right? In the case of alcohol, we're making the ethoxide or alkoxide. In the case of the carboxylic acid, we're making the carboxylate. But in a carboxylate, what can that negative charge do? What can that guy do that can't? It can resonate, right? We can draw a resonance form of the carboxylate. So each carbon, instead of each oxygen has a negative 1/2 charge. Instead of one oxygen having a whole negative charge, we've got 2 oxygens each with a half. So if you look at the electrostatic potential map of this, you see on the top, we've got all that negative charge just in that small little area. And on the bottom, we've got it distributed amongst both of those oxygens. And the more that we can distribute charge, the more stable. All right? So all 3 of these first effects, electronegativity, size, and resonance, are big effects, leading to changes on the course of millions, billions, trillions in acidity. Okay? The fourth thing that can affect pKa is the smallest, and that's the inductive effect. The numbers that I gave you guys at the beginning basically have those first 3 categories built into it. All right? Because I told you to memorize the carboxylic acid, the phenol, and the alcohol. Right? I told you to memorize all the different types of carbon. sp carbon, sp2 carbon, sp3 carbon. All right? The big numbers are built in. The inductive effect, we're talking about a small effect. The largest inductive effect you're ever going to see is going to be like 3.5, maybe 4 units. All right? The inductive effect is a small effect. The inductive effect is a through bond effect. All right? It's basically saying that the sigma bond network creates a temporary dipole to kind of help stabilize that negative charge. Now, it can't move around very much in the sigma bond network, right? So it can't create much of a stabilization. But it tries to help out as best it can. All right? So here you see ethanol versus 2,2,2-trifluoroethanol. Ethanol comes in right around 16. You put 3 fluorines on it, the most electronegative atom out there. And it drops it all the way to 12.4. All right? The inductive effect is a small effect. But what's happening here is this fluorine says, all right, I see that this hydrogen's gone now, and there's a negative charge there. I'll do what I can to help. So it pulls these electrons, it pulls these electrons in this CF bond towards it a little bit. All right? It does its best to pull those electrons. Well, then these electrons get pulled because that carbon's got a little bit of a positive charge now, and so it pulls from its neighbor. It says, I'll do my best. And then this guy pulls a little bit. All right? It's not something that travels more than 4 or 5 bonds. All right? Once you get 4 or 5 bonds away, you're not going to see any inductive effect. And the less electronegative the atom, the less of an effect you're going to see. Right? With fluorines are where you're going to see the most effect. But these are small, small, small little things. Here you can see the effect that the distance has. You got the 2,2,2-trifluoroethanol at 12.4. If you add 1 carbon in between, it drops it to, or raises it to 14.6, drops the acidity. And if you go the further way out, all the way to 4,4,4-trifluorobutanol, the pKa is 15.4, which is virtually unchanged from the 15.9. All right? So it decreases significantly with respect to distance. All right, Drake, what was your question?
So is this set?
No, it's not. So the more electronegative the atom is, the more it can help out. All right, because it creates a partial negative, which creates a partial positive next door, which then allows it to accept a little bit of electron density, that sort of thing. All right, so the larger or the more electronegative it is, the bigger effect you're going to see. Eric? Not really. There's not really anything that you can do that will destabilize it much. The only thing you can do is the reality is there's not much that donates density. You know, most everything we have pulls electron density away. Now, let's then go up here, go and talk about, no, sorry. It's not doing what I want it to do right now. So how can we use these pKa values? Now that we know what pKa is, now that we can look at any compound and predict what its pKa is, how do we actually utilize that? You know, how can we figure out if things are going to react or not? in the first reactions we looked at, we were just comparing everything to water. All right, we have HCl and water going to form chloride minus in the hydronium. And we know that overall the HCl has a pK of -7. All right. We know that it's a strong acid, right? It dissociates completely. And the second one we looked at, it was the acetic acid reacting with water to form the acetate and the hydronium. And we said it's got a pK of 4.76. Now, we can measure those pKa's, but then we can also kind of calculate them as well based off of the numbers we just learned. All right, HCl is -7. H3O plus is -1.74. And so I like to think of these as being battles for a proton. Right? You look on one side of the equation and see what's acting as the acid. You look on the other side and see what's acting as the acid. Assign each their pKa, and then you can calculate the KEQ. All right? On the bottom one here, we've got acetic acid at 4.76. We've got the hydronium at -1.74. So what's the stronger acid here? Hydronium, right? So the hydronium is going to be the one that gives the proton away. So this one's going to be favoring the products, right? So they're going to be opposite each other. And the great thing is, using these pKa's, we don't even have to think about the water being at -1.74. We can use anything. Like here we've got acetic acid, like we said, which was at 4.76, right? And what's the acid from the other side? What's our conjugate acid on the other side? The ammonium, right? And the ammonium was at 9.24. Right, remember all the amines, any of the alkylamines, we said 10.7 to 11 was a good number, but ammonia itself was 9.2. So which direction does this equilibrium lie? To the left or to the right? How many say to the left? Raise your hand. How many say to the right? How many have no clue? All right. Between acetic acid and ammonium ion, which one is the stronger acid? The acetic acid, right? So it's going to be the one that donates the proton. All right? Since it's the stronger acid, this arrow is going to go to favor the products.
Why the arrow's the same one?
Because I was setting you up to ask the question. All right. So the equilibrium arrow here is going to lie to the right. All right. Now, the other thing that's kind of cool is that we can use this to actually calculate the KEQ. All right. Now, again, we're going to have to do some mathematical manipulations here. But remember we said that the KEQ can be equal to the products over reactants, right? So if our reactants was HA and a base, and our products were A minus and BH plus, right? Are we good there? So if we multiply both top and bottom by the hydronium ion, what's that really doing? If you multiply the top and bottom by the same thing, you're multiplying by 1. But that gives us this. All right, which is really Ka over the Ka for HA over the Ka for HB, or the hydronium ion. All right. So that tells us the KEQ is going to be found. Remember when we're talking about logs, if we're dividing, we just subtract. It just means we subtract the pKa's and we get the KEQ. All right. So on the one we were just doing, 4.76, that's the Ka on the left, right? Or acetic acid. Subtract the right, we get minus 4.48. So that's our pKeq. Okay. So then we just take 10 to the minus 4.48, 10 to the minus 4.8 since it's a negative, and that gives us 3 times 10 to the 4th. All right, so we can calculate the KEQ just by subtracting the pKa's and then taking the negative log. Okay, or 10 to the minus of the log. All right. So on this one, what do you think? Is it going to lie to the left or to the right? Talk about it with your neighbor for a second. Turn around. You've got neighbors behind you. Is it going to the left or to the right? To the right? All right. I'm hearing different answers. What's the pK for acetic acid? What about for carbonic acid? 6.36. So which way is it going? To the right. All right. So what's its KEQ? What do we do? We subtract. So we take 4.76 minus 6.36, which gives us what? Negative 1.8-ish. So then the KQ is equal to 10 to the negative 1.8, which equals? Oh. Get it right, Darcy. What is it? 39.8. Okay. So this one's not as large as the last one, right? Our pKa difference isn't as high. But we can use these pKa's to predict whether reactions are going to go in the forward directions or the reverse direction. All right? We'll stop there and we will finish. We just have like 6 slides to go on acids and bases and we'll be done with it. We'll finish those on Monday.